We want to get to a point where you do not need to think about the quantum computer at all. Develop your program however you're going to develop it, and then run it through an optimizing compiler for execution on a quantum computer. That optimization will actually change the algorithmic runtime of the program.
Most applications businesses rely on are complex, with subroutines, loops, etc. Is it possible to run a binary like this on a quantum computer? Not quite, but one company has a tool that identifies portions of code where quantum computing circuits could make a difference, and then manages the necessary handoffs. Find out how pieces of many types of workloads might be running on Qubits soon in this episode of the Post-Quantum World. I'm your host, Konstantinos Karagiannis. I lead quantum computing services at Protiviti, where we're helping companies prepare for the benefits and threats of this exploding field. I hope you'll join each episode as we explore the technology and business impacts of this post-quantum era. Our guest today is the CEO of Horizon Quantum Computing, Joe Fitzsimons. Welcome to the show.
Thanks very much for having me.
Yeah, it's been a while. I first saw you speak like 2 years ago at Q2B. So I'm glad to finally get a chance to connect like this. I know you're in Singapore, so this is the most long range episode we could possibly do as far as the planet goes. So your company is very interesting. We've had on IDEs before, companies with IDEs. We've had on companies doing things like tools that simplify part of the stack, abstract out quantum coding. But you're doing something a little different. So I'm going to want to dig into that today. So let's get started with high level. What does your company provide to the world?
Sure. So we try to build the most capable tools for complex software development for quantum computers. But what we are trying to do, and I think what most people know about us, is that we are trying to go all the way from classical code written to run on conventional computers, and automatically accelerate that on quantum computers, which is kind of an ambitious goal. But fortunately, it's going to take some time to get to really useful hardware. So we have a bit of space.
Yeah. So normally people think of a few pieces of that, right? There's the hunt for the right algorithm. You know, we're trying to solve this business problem. Is there a quantum algorithm? There isn't. Okay, move on. There's that kind of approach. And then there's this idea that if you have classical code and you envision a future where it's going to be part of a workload, and only a little bit of it is going to be helped by quantum, and the rest of it isn't. Kind of, I guess, like what D-Wave does, right, with their approach. So I suspect there's a little of both going on here in helping find the right algorithm, and also maybe farming some to classical. So can you maybe just start like really high level? Are there pieces? Are there blocks like that involve circuits or not?
Yeah, sure. So let me tell you about the whole pathway. What it takes to go from classical code all the way down to something that runs on a quantum computer. And I should say there are gaps in this in terms of what's implemented so far in our system, and I'll tell you what's not at the moment. The first thing you have to do if you've classical code, so working from the highest level down, you need to construct a quantum algorithm to tackle the same task. And generally what people are doing is not that. So you mentioned D-Wave, and there's, of course, other companies that focus on optimization algorithms, for example. But generally what they are doing is offering a quantum optimizer that works in a different way than whatever optimizer you were using before. And so has different behavior, produces different results with different probabilities. Some problems are easy, become hard. Some that are hard become easy. It's just a different thing to what you were doing before, and maybe it's more efficient for your problem. Now, do we know if there's a generic quantum speedup for that? With annealing and things like that, not really. So there's some question marks there. But generally, what most of these efforts are doing is trying to build a library that can replace your optimization library, but maybe with different behavior. Sure. What we're trying to do is have your code function in exactly the same way, so that all of the side effects are the same, so that all of the behavior, you're going to get the same outputs with the same probabilities. You just get them quicker. So if we want to do this, first of all, we need to say, what exactly do you want? You need to specify exactly what the inputs and outputs look like. And the easiest way for us to do that is say, give us code. Give us classical code that implements a solution, and we're going to try and accelerate that. So now you can think, okay, what determines the runtime for that classical code? And it's almost never that it's just an enormous number of lines of code. It's much more often that there are loops and recursive function calls that are what are causing the same bits of code to be reused again and again and again. So what we try to do is we try to break these apart into simpler and simpler blocks. So you might have a large loop within your program. We try to fission that into many loops. So we try to break them down to simpler and simpler pieces until we get to a level where we can actually recognize what each individual piece does. So once we can do that categorization, what we want to do is replace it with a different piece of code that does exactly the same thing, but exploits quantum mechanics to do it more efficiently. In some cases, there might just be a more efficient classical way of doing the same thing. And if that's the case, then obviously you make that replacement too. And then once you've done those replacements, you push it all back together, merge it all back together. And that gives you a kind of hybrid classical quantum program, but not the kind of hybrid programs that you see for variational techniques, for NISQ algorithms, where you're just doing the same circuit again and again and again, but rather a complex program where you're calling quantum programs as subroutines within it. So that gives you the algorithmic structure. And you can ask, where are the speedups going to come from in this? And I would say, what you're doing is you're navigating some of that flow control quicker. And the other thing you're doing is when you have assignments, you're computing those functions quicker. So when you're doing operations on different kinds of data types. More generally, we know that there is a quantum speedup for evaluating fragments of circuit. And what we can do is, if we take that together with the way of speeding up flow control, that gives you an overall algorithmic speed up on the program you have. The next thing you do, that gives you a high-level description of a quantum or a hybrid classical quantum program that does the same thing. Now, you have this specified in some representation. You might expose that as a programming language. So for us, we have a quantum programming language that allows for this kind of complex hybrid classical quantum computation. And then you need to compile that down into something that can execute on hardware. So for us, we go from a kind of basic-like representation. We compile that down, and that might include classical subroutines written in C or C++, something like that get compiled down into reversible quantum circuits. But now we still need to deal with flow control because lots of classical programs have while loops and things like this that you cannot implement as a quantum circuit. So instead, you need to implement them in this kind of concurrent classical quantum way where you're doing simple classical processing on the control systems and you're also doing the quantum processing on the QPU. With measurement results going from the QPU to the control systems, and with the control systems deciding what operations the QPU does next.
So this isn't a simulator. You are actually sending those parts off to whatever you select as a target.
Yeah, so that's where we get to at the moment. Most systems aren't really capable of this, of doing backwards and forwards communication in real time. So what we do instead for these is we have our own runtime environment that will try to execute the program by turning it into a circuit. And most of these cannot be turned into a circuit. So what it does is it makes as much of it into a circuit as it can. It then runs that, gets a sample for what those intermediate variables and measurement results are that it does not know ahead of time. And then it uses those to unroll the circuit further and then reruns the expanded circuit on the system, samples that, and goes back, unrolls a further one, and so on. And it keeps running again and again and again, unrolling the circuit until it gets to a halt instruction. And what it's doing is it's stitching these together with post-selection. So it's ensuring that it gets the same measurement results each time round. And this allows it to simulate a program that branches arbitrarily, that has arbitrary classical computation happening at the same time as the quantum computation. Now, what we would really like to do is to implement this in real time. But it's much more challenging for some systems than for others. For superconducting systems, you need to do the computation extremely quickly because the gate times are fast. For trapped ions, you can be a bit slower. So we took the decision about 7 months ago, to start building up a hardware testbed where we're putting together a quantum computer. Well, we have space for 3, but we're putting together the first quantum computer there from components. So we have a QPU from Rigetti, we have control systems from Quantum Machines, we have a fridge coming from Maybell. We're putting all of those together, and then we're implementing our own runtime on top of this to try to get to that point of doing the real-time runtime environment, to be able to execute this general branching program with general feed forward.
And this is to learn for the future, right? Because you're not actually going to get a level of qubit fidelity or a number of qubits that would blow away what you could do in a simulation, right?
There's not going to be a real advantage from that system. Yep. It's only a 9-qubit processor. Although, actually, because we have low-level control of the system, you can think of it as a bit more than a 9-qubit processor because it has what are called tunable couplers, and those themselves you can think of as almost like a qubit. So in total, there's 21 control quantum systems on the chip that we get to play with. So we're working towards implementing the runtime environment. And the purpose of that is not to have it just with a 9-qubit chip, but so we can scale up to larger systems as they emerge. The thing about all of this is that it takes time. People sometimes think that you should just concentrate on hardware, build good hardware, and then once you have good enough hardware, then start building the software. But that just doesn't work. The economics of that don't work. Because then there's no customers for the large quantum computer for years and years.
Yeah, that's the model of the whole industry right now. I mean, that's what we're all doing in the NISC era, right?
So you need to be building the tools to program these systems, the tools to exploit them for real work at the same time as you're developing the hardware. And for me, I don't see the future of quantum computing as focusing on NISC, on using these kind of variational techniques. I see it as much more like Shor's algorithm, that we want to take those things where we have guarantees of speed up, where we know we're accelerating a program. We know that there aren't instances where it gets worse, and we know that it can behave as a drop-in replacement for what you're doing already, rather than having weird behavior that requires you to retest everything.
So the goal of the way you're building this up is that in the future, you should be able to plug any system into your environment, right? Like, and have it do the quantum part.
Yeah. So, I mean, where things stand at the moment for us is that we can compile and run on quite a wide variety of hardware, on IBM machines, on IonQ machines, Rigetti machines, Oxford Quantum Circuits, and so on. And we do that. We obviously do test runs and so on. But yes, our intention is to be able to target basically as broad a selection of hardware as is possible. However, I should say, when we want to go from classical code to take something, compile it down, execute it as a hybrid program, then obviously some processors have more memory than others. Some can just tackle computations that others can't. So there needs to be a selection process at that point. And we aren't the full way there. So where we are today, what's available in our IDE Triple Alpha, which is currently in early access, is we have a quantum programming language that's a little bit like Quantum Basic. You can have subroutines in it that are written in C and C++, and you can compile that down and run it. You can do this concurrent classical quantum computation through our runtimes. You can compile it down, hit deploy, you get back an API that your code lives behind. So you call that API specifying any inputs that are flagged in your program. It will automatically execute that program on hardware with the inputs you supplied and return the results to you. Actually, if you want to go off and get down in the weeds, you can actually do intermediate communication. So you can read in variables progressively if you want. So maybe if I get this measurement outcome, only then will I ask the user, only then will I ask the API for more information. right? So that you can flag in your program. So it allows you to do things like interactive computing, which are not generally possible, definitely not within circuit frameworks. But because we're stitching these things together, multiple runs, stitching them together with post-selection, it allows us to get around the finite memory time of the existing systems. So it allows us to actually implement some of these in a way that the developer doesn't need to think about at all. It's all taken care of by the runtime environment.
Yeah, that was leading up to what I was going to ask you next. It sounds very much like you're trying to design this for people to not even have to think about the fact that there's a quantum computer in the loop, right?
Yeah, that's what we want to get to. So at the moment where things stand, you very much do need to think about the fact that there's a quantum computer in the loop, right? So within our IDE, within our programming languages, and Hydrogen, as I say, is kind of like a quantum basic. Helium, which is kind of like a quantum basic, and Hydrogen, which is our lower level assembly-like language. Within those, yes, very much you're completely exposed to the quantum computer. It's there as is a kind of simple classical computer that you're also able to interact with, or that you're also able to program that's interacting with your quantum computer. Where we want to get to, we want those who do not want to think about quantum computers to not have to think about them. We want to automatically accelerate it. One of the big advantages to, I'd say one of the big boons for NVIDIA has been the fact that a lot of the GPU computing has started to be abstracted away. That you really don't need to think too much about the GPUs themselves. You don't need to write shaders or for them or anything like this. It starts to get exposed through kind of standard Python libraries and things like this, or MATLAB or whatever, and you don't really need to think too much about the GPUs there. So we want to get to a point where you do not need to think about the quantum computer at all. You're going to develop your program however you're going to develop it, hopefully in a quite simple way, and then you're going to run it through an optimizing compiler that will optimize it for execution on a quantum computer, and that optimization will actually change the algorithmic runtime of the program.
So right now we're obviously in the pre-quantum advantage era.
Yeah.
But are you, with your techniques of optimizing the classical code, are you seeing performance boosts anyway, just because you're taking that extra care before it does the quantum subroutines?
So yeah, I mean, we've done some examples of this. Like, you get advantages everywhere, right? So, what I would say is the path we have for compiling just subroutines written in C and C++, well, taking a function written in C or C++ and turning it into a quantum subroutine, that just does better than people can do by hand. So we've seen some examples of this. There was a paper on options pricing from Goldman Sachs a few years ago, where they had worked out detailed estimates for gate counts. And we ended up re-implementing the most expensive part of that. So if you look at it, it turns out computing a classical function that's just e to the minus x or e to the minus x squared turns out to be the bottleneck for that. So we just looked at e to the minus x. So if you do e to the minus x, I think they were using some circuit constructions from a paper from Microsoft Research from around 2018. And if I remember correctly, it was taking, for the precision they were working at, it was taking around 50, I think for 21-bit precision, which is what we looked at, it was taking about 15,500 gates, Toffoli gates, I should say. And for us, you run it through the compiler, through the C to Q compilation for us. The circuits we were getting out had hundreds of gates as opposed to tens of thousands of gates. So I think the biggest improvement we saw was about a factor of 112 over the constructions they were using that were good constructions for these functions. It's just, we implemented the code. It's not very much C at all to compute it, but there's just so many different branches that get optimized automatically that don't have structure in the way you might look for structure if you were trying to construct it yourself. Like if you were trying to explicitly write down the circuit, because it's just too many gates, right? 15,500 Toffoli gates is a lot of gates. So starting to look for that structure to eliminate and so on, and say, oh, well, in this range, the value of X is too small. So because we're only working to this precision, that means that actually it's always going to be 0 beyond this range. Like, that's just not easy to catch by hand, but it gets compiled out, right? So if you have an optimizing compiler, you start to see that kind of thing. And that's, that's like a significant saving. Similarly, we have explicit constructions for constructing low T-depth circuits, for example, or low depth circuits. So we can do a lot better than you would naively do by hand, or not even naively, than you would be likely to be able to do by hand, unless you really kind of go to the trouble of working out all the low gate constructions and then you optimize it by hand. And it's just going to be very, very difficult to do.
Are you planning on showing a lot of this benchmarking that you're doing in papers, or is this going to be like very closed?
So it's pretty closed at the moment. Okay. I feel like I wrote a lot of papers in my prior academic life. So the benchmarking, to be honest, I'm not sure the best way to do it. The problem with doing it all as papers is that for sure the referees are going to ask you how it works, to explain in detail how it works.
Yeah, that's why I asked if it's closed.
if I look at what has gone on elsewhere in the world, I can look at the fact that Google published the Transformers paper, Attention's All You Need, and gave Microsoft $1 trillion in market cap. That maybe should have been Google's. Depending on
OpenAI was like, yay, let's run to the bank with this paper 7 years later. Yeah,
exactly. So I'm not sure I'm going to replicate that mistake. Maybe different mistakes, but that one I'm hoping not to replicate. At the same time, of course, it's important that people be able to test the system, be able to gain confidence that it's actually working, that it's doing what it says on the tin. But fortunately for things like compiling classical code, you can test it. I mean, you just input-output pairs tell you whether it's correct or not. So that's something that can be objectively verified without actually seeing how the interior works.
So right now you have early access, and we'll put a link in the show notes.
Sure.
So what type of person hits that early access? Is it someone who just wants to see, oh, what's this IDE like? Let me play around with some code I have and see if maybe one day I'll bring it to the quote-unquote boss. Or is it, hi, we're a Goldman Sachs and we want to run a Monte Carlo simulation and see if you can help us? Is it like that level right now? Like how extreme is it?
So in terms of what we get in terms of the early access form submissions we see and stuff like that, it's a mix. So you get people who are students submitting it, or that are just interested for their own personal their own personal interest to try it out. I should say we're very selective at the moment. We have limited capacity. It uses quite a lot of computation. There's still bugs and stuff like that we're working through. So we're slow in rolling it out, for sure. But you also see the other side. You see people applying from large organizations. Some of that you see come in through the early access forms. Other times you get it directly by email. Quantum computing is a small world, so people know each other. And when you know someone, it's sometimes more natural to email them directly, something like that. But what I would say is that of just the early access forms we would have 35 plus large multinationals that have come in that way as well. But, as I say, we're still at the stage where we've only a few organizations that are actually on the system at the moment. We're being slow about the rollout because we want to make sure that when we start to broaden access to it, that it's really rock solid, that everyone has a good experience, that it's doing what they want.
Yeah, I get it. You don't want necessarily a million users right now. That wouldn't make any sense.
Yeah. And we'll run into problems if we have a million users right now. We'll run into infrastructure problems, and there's only a few quantum computers that we can run. We can run on most of the quantum computers, but there's only a few well, not a few, but there's dozens of quantum computers in the world, not millions. So it's yeah,
You better watch out. This podcast is growing. I don't know. A few people might hate
maybe
you.
hundreds. I should probably say hundreds.
So, has it become a situation now where? Oh, okay. So first of all, the early access, is it free for depending on who you are, or
So
is there a cost?
as I say,
automatically no matter?
we've only been working with a small number of organizations, and how we've worked with them has been a little bit different. Of course, we are very interested in working with hardware companies. At the present time, we want to make sure we support the maximal range of hardware and that's integrated and so on. But at the same time, we have software companies that are using us to develop at the moment too. Yeah, so it's early access, so we're not charging them for that, but that will change over time. I'm afraid. I took money from venture capitalists. I need to return something at some point.
Of course. But have any of the like bigger companies who have played with it said, "Hey, we just matched Garobi with this. We like it. When can we roll out?" And now all of a sudden, like you're ready to have a contract. That kind of thing?
Where we stand, where our focus is not on enterprise engagements at the moment.
Okay.
I want to be clear. Our focus is on partnering with the hardware companies. And the reason we want to do that is because ultimately our ambition is to become the default software layer. Let's say the default software development and deployment layer. And in order to do that, we need to build the best development tools we can, the best development tools that are available. And we need to prove to the hardware companies that we create value for them. Because we want them to make our tools available to their users long term, right? Not tomorrow, long term. So that's where our focus is right now. It's on gaining technical lead and on establishing partnerships with the hardware companies, because really we don't want to be in a position where we're trying to sell to large enterprises before there's a real quantum advantage. Because, I mean, what value are you creating for them? You're creating a press release. So are they going to be a long-term customer? Are they, okay, yeah, post-quantum advantage, sure, but there's not really, you're not gaining much. You're turning yourself into a consulting company if you do that. And that hasn't worked out so well in the field so far. So I'm sure there will be.
My company's a consulting company.
I'm sorry. Sorry. I don't mean it that way, but I guess what I mean is, like, if you take a lot of money from VCs and you end up having to pivot towards consulting, or you end up that most of your effort is going into consulting projects, it's very hard to gain the margins that you would need to return, like for those investors to see a return on their investment. And that has hurt companies. I mean, you've seen it with Zapata, for example, that it's clearly been a contributing factor there. So for us, we stay as far away from that as we can. We focus really on how do we progress the technology, how do we make inroads with the hardware companies, and how do we get to a real quantum advantage as soon as we can. And then we can worry about the enterprise engagements. Now, sure, we care about enterprise use cases before then and so on, but actually it doesn't make all that much sense for us to focus on enterprise right at the moment.
So in a way, you're learning as much from your users right now as they are from experimenting with the tool,
sure.
Right?
Yeah, of course. Yeah. I mean, really we are. We want to know what are the things you want to be able to do. We built something which we think ticks a lot of boxes, but sometimes there are things that are not satisfied. So I can give you an example of this, which is that depending on the type of user you are, you may want to be able to address the physical qubits on the device or address qubits that are not physical that will get automatically laid out by an algorithm for you. Or, depending on how complex your software is, you may want dynamic memory management, where you say, hey, I need a qubit, and the program, like the runtime, gives you a qubit. It says, here's a free address, right? And if you're building a circuit, that doesn't matter. So, like, if you're using, if you're doing something that is just a quantum circuit, you can count the number of qubits ahead of time. You can have an algorithm assign the qubits ahead of time. But if you have this kind of branching program, well, in one branch, it might use more memory than in a different branch. So it may not be computable what the maximum amount of memory that's used is. You can think of a simple example. You have a Turing machine that runs, and if it halts in an accepting state, then you assign a whole chunk of, you assign 2 qubits, and if it doesn't, then you assign 1. And to solve that, you need to solve the halting problem to know how many qubits the program uses. Yeah. Or if it halts after an odd number of steps versus an even number of steps, or whatever you want it to be, but you can make that an undecidable problem. So you would think, oh no, you can just, you should just be able to work out how many qubits it uses. But for complex code, it becomes impossible. And if you try to avoid that, then you limit the functionality and you have something that's not Turing complete, that can't do everything. And like if you say, okay, no, I'm gonna directly implement my Turing machine, just pre-assign all the memory, but then you need an infinite amount of memory. So that doesn't work either. So you actually need to do what a modern operating system does, for example, where it's going to manage the memory for you. Mm-hmm. But there's a very big difference between that. You cannot both have that and be dealing with the physical qubits. Except maybe you can. And so now we've started to enable a kind of hybrid approach where you can pin certain qubits and have others dynamically managed for you. But there's really a big stretch in between. And we had skewed more towards dynamic allocation. Like, hey, we're going from classical code. The user's not going to want to be picking physical qubits on the chip. But if you care about characterization experiments, if you care maybe about error correction or something like that, then you really do want to pick the physical qubits on the chip. So, to enable that, we got feedback on that. We enable qubit pinning. So you could refer either to a specific physical qubit, or you could ask for a dynamically assigned one. And if it's dynamically assigned, you want it to not be one of the pinned qubits and so on. So, feedback from users is really important because we want to make sure we are building the most capable tools for complex software development. And it's hard to do that in a vacuum.
And we have, although it's all kind of in a vacuum, right? Depending on the modality. Anyway, and on that topic of modality, before I let you go, obviously folks are going to try and see if they qualify for access or whatever. Is there a modality of quantum computing that, whether it involves a vacuum or not, that you're most interested in working with that you haven't had a chance to work with yet?
Sure. So, at the moment, we have superconducting and trapped ion systems that we've been compiling and running on. I'd love to be running on neutral atoms. I'm also super. You were going to say that. Yeah. They're really interesting. Also interested in photonic quantum computing as feed-forward starts to become available. The problem you have when you don't have active feed-forward is that you end up with boson samplers, and they're just not as programmable as a general gate model or measurement-based quantum computer or whatever it happens to be. And it doesn't make that much sense to have these complex programming languages where you can, compile some C code if you can't actually run it because you can't do an AND gate.
I still have to do an entire episode on feed forward. That's something that's like untapped territory in many ways.
So it's going to be, that's going to be super interesting to us. It's just, what the state of readiness is on that. The neutral atoms are the ones where it's very clear that they're very very interesting, very capable systems that are becoming available at the moment.
Yeah.
And
We've got logical qubits there for sure.
Exactly.
All right. So you heard it. Listeners who are involved in Neutral Atom, feel free to reach out as well. So Joe, thanks so much for coming on. Really appreciate it. And good luck. And I hope to see this start manifesting on systems. That'd be pretty great.
Thank you very much.
Now it's time for Coherence, the Quantum Executive Summary, where I take a moment to highlight some of the business impacts we discussed today, in case things got too nerdy at times. Let's recap. Horizon Quantum Computing has the audacious goal of automatically accelerating classical code on quantum computers. They're trying to create a bridge between the programs we use today and the quantum future, potentially making the transition seamless and painless. Think of it like a universal translator, but instead of languages, it's translating between classical and quantum computations. Horizon takes code designed for classical systems and automatically optimizes it to run faster on classical systems. Then it identifies parts of the code that can be passed off to quantum systems. They are doing this by breaking the code into smaller pieces, categorizing it, finding more efficient ways to perform the calculations, classical or quantum, and then handling execution. This could revolutionize the way we interact with quantum computers. The approach works with multiple modalities of existing quantum computers, but Horizon is also putting together an in-house quantum computer to experiment with the handoffs in a controlled fashion. Their IDE, currently in early access, is designed to abstract away the complexities of quantum hardware. The aforementioned handling and optimizing of code pieces with their solution already allows for some performance boosts, but Horizon wants to become the quantum future's default software development and deployment layer. Visit the link in the show notes to see if you can try it out. That does it for this episode. Thanks to Joe Fitzsimons for joining to discuss Horizon Quantum. And thank you for listening. If you enjoyed the show, please subscribe to Protiviti's The Post-Quantum World, and maybe leave a review to help others find us. Be sure to follow me on all socials at Constant Hacker. That's Constant with a K, Hacker. You'll find links there to what we're doing in quantum computing services at Protiviti. You can also DM me questions or suggestions for what you'd like to hear on the show. For more information on our quantum services, check out Protiviti.com or follow Protiviti Tech on Twitter and LinkedIn. Until next time, be kind and stay quantum curious.